The Proterozoic world now had an oxygen-rich atmosphere, creating a more stable, evolving chemical balance. High above, the ozone shield grew stronger, a robust guardian that absorbed lethal solar radiation. Beneath the waves, simple prokaryotes still dominated, but a new cellular architecture was about to emerge. Then came a pivotal moment. In a primitive ocean, one cell engulfed another, beginning the partnership of endosymbiosis. The captive, once a free-living bacterium, was not digested. It became the mitochondrion, a biological engine for its host. Energized by its new partner, the host cell innovated, evolving a nucleus to safeguard its precious genetic code. With these changes, the eukaryotic cell was born. It was larger, more organized, and a revolution in life's design. The age of alliances was not over. Later, some eukaryotes would repeat the process, engulfing photosynthetic cyanobacteria. These new captives became chloroplasts, effectively turning their hosts into self-sustaining miniature solar power plants. From these innovations, the protists exploded onto the scene, a new kingdom of life displaying astonishing diversity. Unlike prokaryotes, eukaryotes had flexible internal skeletons, making them dynamic predators capable of changing shape. Many eukaryotes also evolved sexual reproduction, shuffling genes to dramatically increase variation and speed up evolution. The next step toward complexity was organization, as individual cells began to live together in coordinated colonies. Within these colonies, a division of labor emerged, with cells specializing in certain tasks, a prelude to true multicellularity. Soon, this cooperation gave rise to the first simple multicellular organisms, likely resembling little more than filaments of algae. Meanwhile, on a planetary scale, Earth's great landmasses were in constant, silent motion, driven by plate tectonics. Ancient continents, the scattered remnants of earlier worlds, began a slow-motion dance of convergence across the globe. Eventually, they collided in a geological event of unimaginable scale, forging the great supercontinent known as Columbia. Columbia united nearly all of Earth's continental crust into a single immense body, dominating the world map. Life, ever adaptable, responded to this new world, evolving to survive its vast interiors and thrive along its coastlines. In the sunlit coastal seas of Columbia, complex ecosystems of early eukaryotes and bacteria flourished together. The existence of this massive landmass had a profound impact, altering global climate patterns and redirecting ocean currents. These new environmental pressures spurred on the eukaryotic revolution, accelerating the exploration of new biological forms. Their efficient energy production from mitochondria fueled this diversification, allowing for larger bodies and more active lifestyles. For hundreds of millions of years, the supercontinent Columbia stood as a testament to the deep geological rhythms of Earth. But supercontinents are not eternal, and trapped heat from the mantle began to weaken Columbia's foundations from below. The two essential ingredients for animals were now present: an oxygenated world for fuel and complex cells for machinery. To a casual observer, life on Earth was still simple, but the potential for all future complexity was finally unlocked. Earth continued its ceaseless transformation, a planet defined by the dynamic interplay between its geology and biology. The rise of complexity had truly begun, setting the Proterozoic stage for the spectacular evolutionary acts yet to come.